Welcome back. Today we're going to be discussing free body diagrams here in POE. Free body diagrams. A free body diagram is a visual representation of forces and the object's interactions. Individual objects or members are isolated from their environment or system, illustrating all external forces acting upon them. Over here we're showing a bridge, a truss system that we'll be dealing with later. And they're showing that there are upwards forces pushing to hold the bridge up, and then there's the load that'll be pushing the bridge down, and there can be forces that are pushing it to the right or to the left as well. With the pulley, we know that there will be forces that are pulling down on it, and there can be several forces that are pulling up on it. And then with other systems, we can have multiple loads. We can have a very simple bridge where we have multiple loads. We have forces pushing up and holding it, and we could have forces pushing it. But those are just giving us a couple examples of free body diagrams. Free body diagram components. A straight line push or pull acting upon an object. Vector quantity has direction and magnitude. And we introduced this yesterday. But a vector quantity has direction and magnitude. In this, we have the direction, and what we haven't got here is a magnitude. And if I were to just put something like 15 newtons there, now we've got a magnitude, and this could be theta, which is giving us the direction. Direction is illustrated by an arrowhead. Magnitude is illustrated by the length. So this length would want to be proportional. So if I wanted to do one that was 30 newtons, I'd have to make it twice as long. And then that would be able to, we want to keep all arrows proportional to their magnitude from that point on. Moment. Free body diagram components. Now the one thing we haven't talked a lot about this trimester, but we've slowly kind of introduced to you, is moment. Moment is the twisting effort about a point or axis when a force is applied at a distance. In our PLTW classes, our POE classes, they're going to show that the red is going to be representative of a clockwise moment. The red, or the blue, would be a counterclockwise moment. An arc with an arrowhead acting about a point, indicating direction of this moment. Well, we haven't talked a whole lot about moment for a while. Moment equals force times distance. Now, some of you are saying, I thought work was equal to force times distance. That was, but that was for something that was parallel. Moment is when we're talking about something that is perpendicular. So this takes in a lot of circumstances that we said that weren't work because the force and the distance weren't in the same direction. Well, now this moment is when we have a force. Over here is a force being applied in one direction, and the distance is in another direction. So a wheel or a lever, wheel and axle, a lever, those are all examples of moment. A stack of 3 books, each weighing 5 pounds, is sitting on the top of a table. Draw the free body diagram, the FBD, of the top book. Well, as we see here, what they're showing us is they've drawn the isolated object. This is just this top red book. When an object is in contact with and is supported by a second object, the second object can be replaced with a normal force, which is perpendicular to the surface of the second object. For some of you, this normal force is going to be different, but or new, not necessarily different. In this case, we're talking about the normal force. So it's the reaction force pushing up on the book. So this right here would be what we call the normal. All right. This is what's causing it not to fall. This is the force that's pushing up. And sometimes this is difficult for students because they think of things pushing up going on from the bottom, and it is, but the net is it's pushing up on the object. Remember, this right here is our red book over here, the PLTWDE book as they're showing. So this is the red book. And this force right here that's pushing up is representing the force of the table and the 2 books that's pushing up on it. There has to be this normal force, otherwise the weight of the book would just fall. It would be falling, because down here we have its weight. And a lot of times we'll subscript this as F sub W. And this is just telling us the normal and the weight. Now, in this case, label objects and forces. Well, the book is here in the middle, and the normal is 5 pounds pushing up, and the weight is 5 pounds pushing down. Well, how do we know they're both 5 pounds? Well, earlier it told us that the book weighed 5 pounds. So we know the weight has to be 5 pounds. But how do we know up here that the normal is 5 pounds? Well, you can look at the book and say, is it moving? No, it's not moving. So what that tells us from yesterday is that it must be in a state of equilibrium, which means that the force pushing down has to be negated or equivalent to the force that's pushing up. Otherwise, the book would be moving down. If the normal force was greater, then the book would be moving up. It would be accelerated in the upwards direction. Free body diagrams. Label the dimensions. For more complex free body diagrams, proper dimensioning is required, including length, height, and angles. So we had a very simple one over here to the right with the book. Over here to the left, you see a much more complicated one where they're giving us some lengths, some angles, and many more different things that are happening here. Alright, create a free body diagram for the sled pictured below. Well, let's go over these. A lot of times when it comes to a free body diagram, we'll just simply replace the object, any object, whether it's circular, whether it's round, with just a simple box. On here, there are some different forces that are being applied to this object. The person that's pulling, the applied force, and they've got FAPP, and it's at a certain angle they've called theta, so they've got it coming off the box at theta. We've got the weight that's pulling down. Obviously, there's a friction or a contact force called the normal here. That's why the F of N. A lot of times we'll just put N, but the normal force is what's pushing up on it, and the force of friction, which is resisting it. Now, we'll stop at that point. I don't want to go any more explanation. Okay. Create a free body diagram for the refrigerator pictured below. Well, again, you've got a couple of forces that we're going to always be talking about. Simple forces that you need to always be looking for is where is the normal being applied. There's got to be a normal if it's on an object. If there's contact being made, then there's got to be a normal. There's what we're going to call the frictional force, FF. There's frictional force. A third one, and I don't know how you can get away from this. There might be a few examples, but the weight. And then typically the applied force. So these are going to be our most common forces that we look to put on a free body diagram. And if you look at our free body diagram over here to the right, we've got these 4 forces here again. Okay, this is a much more complicated system here. What they've done is created a full free body diagram of both of these masses. What I want to go into is on the top, on mass 1, which is over here, mass 1. All they're giving us here is, they've introduced a new one, our 5th force, and that's a tension force. And they've also got weight. Well, why don't they have a normal? Why no normal on this one? Well, because there is no contact. It's not sitting on anything, all right? So that doesn't exist. So there is no normal for it to be happening. That's why there's no normal. There's no friction. Why is there no friction? Because it's not sitting on anything again. So the new force that we're introducing here is the tension force. Down here at the bottom, we look at force 2. There are 2 tension forces. There's these 2 ropes that are pulling up on it. And then we have here the weight, all right, the second weight, that's why it's W2, the second weight plus the weight of the pulley. Okay, well, that finishes our notes for the first part, the first of the 2 parts. When we come back, we're going to be talking about free body diagram reactions as we discuss the different types of reactions that can happen. I'll see you on the flip side.